Howdy, howdy, this is Mr. Potter. Today we're going to be talking about piecewise functions. And piecewise functions are a good thing to know because sometimes a explicit function like we've had before, which is f of x equals one algebraic expression, isn't enough to really describe a situation. Sometimes we need more than that, and so we'll often use a piecewise function to describe this. So we're going to start with what is a piecewise function. So a piecewise function is a function that satisfies a different definition depending on the domain indicated. And one of the biggest ones that we see is the absolute value function, y equals the absolute value of x. And we're familiar with what the graph of y equals the absolute value of x looks like. It looks like a line that's been bent. But I can really think of this as two different parts. I can think of it as this part here, just y equals x, but on some domain. And I can think of the other part, this part over here, as y equals negative x, again, on some domain, like that. And so I could write this as a piecewise function where I'm basically saying that it satisfies a different definition depending on the domain indicated. And I have two domains that I'm dealing with here. I'm going from negative infinity to 0, which is this white portion over here. And I'm going from 0 to infinity, which is this yellow portion over here. So I could think of y being defined as negative x for this part of my domain, and as a positive x for this part of the domain. And so when we're talking about a piecewise function, we're talking about something where different domains means that my function is going to be equal to a different expression, a different evaluation that's going to be used there. There is a more complicated one called the step function. It's also called the greatest integer function. Or basically we're saying that y is equal to the greatest integer less than or equal to x. You'll see these double brackets being used for that. So I'm really saying here y is the greatest integer less than or equal to x. So if I was to look at this from a table standpoint, if x is 0, then the greatest integer less than or equal to 0 is 0. If I was at 0.5, well, the greatest integer less than or equal to this is 0. Even if I'm at 0.9, that's going to be 0. But as soon as I bump to 1, the greatest integer less than or equal to x is 1. And I can take that all the way up to 1.99, and that's still going to be 1, but as soon as I hit 2, I bump up to 2. So in other words, if I was to look at this from a graph, starting at x equals 0, I'm going to keep, let me get a different color here. Starting at x equals 0, I'm going to keep going until I hit right before 1, because as soon as I hit 1, boom, I bump up. And I'm going to keep going till right before I hit 2, because at 2, I bump up. And so we call this the step function because the graph looks like a whole bunch of steps. And actually, these steps continue into the third quadrant. I can call this a piecewise function because I can say y is equal to a whole bunch of things. I can say y is equal to 0 if 0 is less than or equal to x is less than 1. I can say y equals 1 if 1 is less than or equal to x is less than 2. Basically, using this definition, I can come up with different domains and have my y be defined differently. Of course, this is a more complicated version because it actually goes on infinitely. This will keep on going up, this will keep on going down, and my domains, likewise, will keep going up and down, respectively. So the step function is another function that is a good way to represent a piecewise function. But we actually deal with these quite a bit in real life. So let me talk about this cell phone plan. Currently, there's a cell phone plan that I'm aware of that costs $75 a month. Plus, it's going to charge you $10 for every gigabyte over 10 gigabytes. So if I wanted to look at what this looked like on a graph, I know that if I'm at 5 gigabytes, 10 gigabytes, 15 gigabytes, 20 gigabytes, this graph is going to start at 75, and it's going to stay at 75 until I hit 10 gigabytes, and then it's going to go up $10 for every gigabyte over 10. So that's going to go up, that's 5 gigabytes, that would be $50, that's $125. And then it's going to go up some more, so that's $175, and then it's going to keep going up some more, and that's going to be $225. So I've got a piecewise function, the left part of this graph, the graph that's constant here. Let me do that in yellow. This part that's constant, I could say y is equal to 75 for 0 less than or equal to x less than 10. And I can say that it's equal to 75 plus 10x for 10 less than or equal to x less than infinity. So I'm really looking at this and saying, okay, well, here's my piecewise function. I've got the yellow part here, and then I've got this part that I'll do in white, which is when I've reached my limit and I'm actually being charged on a per gigabyte basis. And of course, this happens in real life. It's not just cell phone plans. There are lots of other plans that behave this way. So step functions are actually very useful in talking about things in the real world where for one interval they behave a certain way, but for a second interval they behave in a much different way. So the biggest thing that we probably want to talk about in this video is how do we go about sketching a piecewise function. So let me go ahead and write a piecewise function over here. I'm going to go ahead and say y is equal to the following definition. I'm going to say it's x squared for -2 less than x less than 2. I'm going to say it's equal to 3 for 2 less than or equal to x less than 4. And I'm going to say it's equal to x minus 2 for 4 less than or equal to x less than 6. And by the way, it's important to note that these domains don't overlap. And it's okay if they overlap at a point, but only if these two graphs actually have the same value. So I can't really put equality here because 3 is not equal to 3 minus 2. And I can't put equality here because 2 squared, which is 4, is not equal to 3. So I can't use the equality on those points. I need to make sure that my domains don't overlap. So I really have 3 graphs here. I have this graph here, which I know what the graph looks like. I know that if I'm dealing with from -2 to +2, I'm looking for a parabola that's going to go through the origin, it's going to hit at 1, and then it's going to go up to 4. So it's going to hit at 1, hit up to 4. So it's going to look something like this. But keep in mind here, I'm going to have a hole. And that's for this part of my graph. For the second part of my graph, for y equals 3, I'm going to be here at 2 and keep going until I hit 4, and it's going to be solid, solid, solid until I hit 4, and then I've got a hole here. And so here's that second part of the graph. Finally, for my third part of the graph, for x minus 2, I actually want to go over to 4, and 4 minus 2 is 2. 5 minus 2 is 3. 6 minus 2 is 4, but that's going to be a whole, and so I'm going to have a graph that looks like this. So when graphing or when sketching a piecewise function, you probably want to sketch each part separately on the same axis. So really what's happening here is that even though my domains are the pink domain, the yellow domain, the white domain, in reality I can think of this as being one graph that's going to start here, trace this parabola to its hole, then go to this yellow and trace it to its hole, and then here and trace it to this hole. And that's what this whole function would look like, this graph that I've got in blue. Now, each of the pieces, the pink piece, the yellow piece, the white piece, each of those separate pieces are going to be easy to draw separately. But what I'm really looking to do here is I'm really looking to combine everything into one graph. So that's our discussion about piecewise functions. I really wanted to finish up this lesson by talking about the parent functions that we talked about a couple of days ago, talking about their domain and range. So some things to keep in mind, we talked about this earlier, whenever we're dealing with polynomials, there's some behavior that we can expect. First, the domain is always unrestricted. In other words, whenever I'm dealing with a polynomial, it should be from negative infinity to infinity. And when I'm dealing with polynomials, my range is affected by the degree. So in other words, odd degree, in other words, if the highest power is an odd number, they're going to have unbounded range. In other words, my ranges are going to go from negative infinity to infinity. Even degree will have bounded range, but it'll be infinite in one direction. So I could think of y equals x squared, that's a parabola. It's bounded. It's never going to go below 0, but it will go infinite upwards. If I think about y equals negative x squared, that again is bounded. It's never going to go above 0, but it is going to be unbounded on the infinite aspect. So we're going to be talking about parent functions and their domains and range. And by the way, keep in mind when I'm talking about even, 0 is an even number, which is important when we're talking about our constant function. For a constant function, our domain is all real numbers, so from negative infinity to infinity. My range, however, is just going to be y equals whatever that constant is. So for us, remember, for our parent function for our constant, y equals 1 is really our range. When I'm talking about a linear, I'm going to be going from negative infinity to infinity. And because linear is really x to the first power, this is going to be unbound as well, infinite. So from negative infinity to infinity as well. When I'm dealing with a quadratic, again, it's polynomial, so it goes from negative infinity to infinity. But because it is a even power, my power is 2, I'm going to have a bounded range. So 0 is as low as it goes, but it goes forever upwards. And similarly, when I'm dealing with a cubic, then cubic is an odd number, x cubed. So it's going to go from negative infinity to infinity and negative infinity to infinity as well. So again, the unbounded domain on either side, the fact that if I'm dealing with a even polynomial, which I was here and here, my range does end up being bounded. We do have other parent functions to look at, though. So let's talk about some of those. We have the absolute value. And for absolute value, my domain is from negative infinity to infinity, because there's no restriction on what I can put between these parallel lines. The only restriction that I have is that the value must be greater than or equal to 0. And that's because my graph, remember, is that V shape. There is a lowest point on that graph, and that lowest point is going to be on the x-axis. When I'm dealing with an exponential, when I'm dealing with something like 2 to the x power, raising a number that's positive to a variable, I'm always going to get something that's positive, but there's no restriction on what I can put up here. So my domain is going to go from negative infinity to infinity. My range, however, is going to go from 0 to infinity, because raising a number to a power, even if it's a negative number, that just means it's going to go in the denominator. And we know from our dealing with fractions that I can never have a fraction actually be equal to 0 if the numerator is not 0. So when I'm looking at this graph, I'm looking at a graph where this exponential graph is going to get closer and closer and closer to the x-axis without ever actually touching it. There's always going to be some gap there, even if it's a very small gap. So we have the reciprocal functions. The reciprocal parent function, that's our 1 over x. And of course, we talked about in our last video how we can't divide by 0. 0 is a bad point. So x not equal to 0 is going to be my domain. I can think of my domain going from negative infinity to 0 and 0 to infinity. And again, this fraction can never be equal to 0 either. So my range is going to be y is not equal to 0. In other words, going from negative infinity to 0 and 0 to infinity. The next one we have is the reciprocal squared. And notice, because we're dealing with a 1 over x squared, this x squared behaves a lot like our even degree polynomial. So because of that even degree polynomial, we know that y is going to end up being strictly greater than 0. In other words, from 0 to infinity. Whereas here, my domain is still, the only restriction is that I can't divide by 0, so x cannot be equal to 0. The other parent functions that we have are our square root and our cube root. And again, we've talked about the square root in our last video. In our last video, one of the things we noticed, of course, is that what's inside the square root can never be negative. So I really want to make sure that for our parent function, where it's just the square root of x, x must be greater than or equal to 0. So in other words, we're going from 0 to infinity, but we can actually hit that value of 0. For our range, the same thing happens. I can't get a negative number out of a square root, so y has to go from 0 to infinity, inclusive on the 0. For the cube root, though, we end up with an interesting problem. I can take the cube root of a negative number. I can take the cube root of negative 8, and that's a negative 2. So one of the things I notice is that I can take the cube root of a negative or a positive number or 0. So again, my domain is going to go from negative infinity to infinity. And similarly, because I can get negative numbers out, I can get positive numbers out, I can get 0 out, my range likewise will go from negative infinity to infinity. So this is one extra aspect that we need to know about our parent functions. We need to know domain and range, because we'll often be needing to take these parent functions and put them together to make piecewise functions. Once again, this is Mr. Potter. Thank you for watching. Have a great day.